Hey everybody, this is Mr. Ainsworth, and we're going to get into lesson 9 here on exponential functions, and we're going to get into a topic called exponential decay, all right, where the base is less than 1. So let me remind you of something here. I'm going to go back to one of our previous lessons. This is what's cool about technology here. Exponential growth is 1 plus r, where the base is 1 plus r, or greater than 1. And decay is when it's 1 minus r or less than 1. Okay, actually, let me go back further. Okay, here we go. So when the base is less than 1, like 1/2, you get a decay type of situation where the function decreases over time. And if it's growth, okay, it's an increasing function. The base is bigger than 1, like 1.5 or 2 or 3, and it's an increasing function over time. All right. So what we want to do now is take a look at another cool example here, something that you could be familiar with here. If you play tennis or been involved in a tournament, this will sound familiar, okay? So check this out, exponential decay function. All right, each year the local country club, all right, if you belong to a country club, sponsors a tennis tournament. All right, this is for all you tennis players. Okay, the play starts with 128 participants. So this is the start. Oh, by the way, this is a video here, so if I go too fast, you can always pause and play me all the way through so you can keep up with me here. All right, so we start with starts with 128 participants, you know, people that are playing in the tennis tournament. During each round, okay, listen to this, half of the players are eliminated. They're gone, okay, half are gone. And that's important here, half of the players are eliminated. The question is how many players remain after the 5th round? You know, what is this value here? I don't know what it is, and then we got to figure that out. Okay, so let's do this by looking at patterns here. We're going to actually calculate it here by hand. Let me see. If a half, that's the key word, if a half remains or a half is eliminated, okay, that's a better way to say it, then what we need to do is take first a half of 128. We need to multiply it by 1/2. And we know that a half of 128, all right, is 64. So a half of 128 is 64. You got to take a half of 128 to get to 64. Or you can take 128 divided by 2, because a half means divide by 2, and you get 64. And then you got to divide it by 2 again. Or you can write down times 1/2. When you take a half, you divide by 2, or you multiply by a half. The same thing, okay? And 64 divided by 2 is 32. So you have 32 players left after round 2. Remember, the top here is the rounds. Okay, then you got to divide it by 2 again. All right, and you get 16. Just do this on the calculator too. And by the way, we're using technology here, so check this out. So let's pretend like you want to use technology. Suppose you had a hard time dividing by 2 in your head. Okay, no big deal. Since you have the calculator at hand, okay, divide it by 2 and hit enter. Divide it by 2 and hit enter, and then hit enter again, and it'll give you all the values here. 64, half of that is 32, half of that is 16, half of that is 8. By the way, these are powers of 2. They should look familiar, because we've been developing these all this time. So we want to divide by 2 again. You get 8 and divide by 2 again. All right, because we're taking half here, which means 1/2 times by 1/2, or divided by 2. They're synonymous here, guys. So basically there's 4 players remaining after round 5. This is the round. All right, and this is the number of players, 4 players. So go ahead and label that. Round 5, there's 4 players left. All right, and that's what I said down here too. Okay, so you can use the technology if you need to, or you can just do it by yourself. All right, and these numbers look familiar because these are powers of 2. All right, so let's take a look at patterns here. 2 squared, let's switch to red. Grab your red pen here. 2, we know that 4 is 2 squared. 8 is 2 to the 3rd. 16, well, guess what? That's 2 to the 4th. 32, that's 2 to the 5th. We know this because we've talked about powers of 2 so much. All right, 64, 2 to the 7th, and 128, 2 to the 8th. Look at the pattern there. So we can figure out what's going on here. What we want to do is figure out what can we do to 128 to get to the number of players, given the number of rounds. Okay, now we know that we started off with 128. And going back to our function here, a sub I here, a sub I, is our initial amount, I standing for initial. Well, in this case, a sub I equals 128. So we know that the function looks like 128 times something. Our base here, which is 1 minus r, because it's decay now, okay, 1 minus r, which equals the base, is equal to, well, let me see, the rate of decay is half, okay? So right here, r has got to be 50% because half is 50%. We should know that by, previous experience. So the rate of decay is 50% because we're reducing this by half, and that's 0.5. So if we substitute that in, we get 1 minus 0.5, or 1 minus half raised to the x power. So what do we get? Y is equal to 128 times, well, let me see, 1 minus a half is, it's a half. So you can write it as 1/2 to the x power, or you can write it as 128 times 0.5 to the x power. So if we wanted to calculate the number of players after 5 rounds, I could substitute 5 in this. So let's do it for funsies here. Clear this out. Take 128. Let's take it to 0.5 raised to the, well, let me see, round 5. Take it to the 5th power. Holy cow, we get 4 players, which is our answer. So we can use this function here to calculate the values. All right, let's double check here. After round 4, we know it's 8, right? So let's check it out. 128, all right, times a quantity, 0.5 or 1/2. You can enter in 1/2 if you like, and take it to the 4th power. All right, let's calculate it. 8. Holy cow, that's what we got earlier. Listen to that, man. You can use this function here to calculate whatever you need. All right, so we got our function here, so let's use it. All right, let's use it to our advantage. All right, so the question is, how many players after 5 rounds? Okay, so our function looks like y equals 128, our starting amount, times 0.5 to the x power, or you can say 128 times 1/2 to the power of x. Obviously these are the same. And 1/2 and 0.5 is the same value. The question is, after 5 rounds, how many you have? Well, we already know that. I already calculated that up here. The answer is 4. So after 5 rounds, the answer is 4. But the question is, how many players after 6 rounds? Let me see, half of 4 is 2, so probably the answer is 2, but let's go ahead and calculate it. All right, 128 times 0.5 to the 6th power, because again, x is 6 for 6 rounds, right? Holy cow, it's 2. All right, so it's 2 players left. Oh my gosh, we have to divide by 2. This is hard stuff, man. Okay, half is remaining. Half remaining. You got to read the problem again, okay? Half remaining. How many players after 7 rounds? This is a really tough question too. Let me see, what's half of 2? Oh, I don't know. Let's figure this out. You got to take 2 divided by 2. It's a really tough number. Let's calculate it. All right, take 128. Oh, let me go back there. I got to hit the right keys. Times 0.5 or 1/2 raised to the 7th power, because we're after 7 rounds here. Let me see. What's half of 2? Ooh, I don't know. Let's figure it out. Oh, it's 1. Okay, half of 2 is 1. So there's 1 player left, and guess what? It's the winner. Okay, the winner of the tournament. Check that out. That should make sense. Winner of the tournament. That's why I put this in here. The question was how many players left of the 5 rounds, but I thought it'd be kind of nice how many players win the tournament. Well, there's only 1 player, right? 1 player remains. That's what happens typically when you win a tournament. One player remains. Okay, so let's graph this situation here. All right. We've got first round, 0 round, first round, second round, third round, 4, 5, 6, 7. This is rounds. All right. And this, my friends, is the players. Number of players. So 2, 4, 6, 8, 10, 12, and so on. So how many do we start off with? Ooh, 128. I'm going to have to change. The scale here because obviously we can't fit all those players on here. So we're going to have to change the scale. See, you have to be smart about these things and you have to use the techniques from the past. So we can't count by ones because you can't get up to 128. So how about by tens? Okay, so here we go. So 5, 10, actually by 5. So this is 5, 10, 15, 20, 30, 40, 50, 60, 70. Ooh, still didn't work. I'll tell you what. Let's make it easy on ourselves here. Let's just graph most of the points, okay? Let's graph all but the first one here, okay? So this is 1, 64. So let's go ahead and graph that. 1, 64. Okay, here's 1, 60. That's 165. Okay, 164. So there's 1, 64. All right, and then what's left over? Let me see. 2, 32. All right, here we go. 2, 32. No. Oh, no. Okay, that's 35. 32 is obviously less than 35, so right about there. Estimate. And then half of 32 is 16, so 4, 16. No. Oh, I didn't do that right. 1, 64, 2, 32. Where's 32 again? Okay, right about there. Okay, and 3, 16. Let me see if that's 15. Then 16 is right above it, right? All right, and then 4, half of 16 is 8. 8's right about there. It's less than 10. 5, half of 8 is 4, so right about there. And then 6, 2, right about there. 7, 1, the winner. All right, now check this out. If you graph this function, you got to put the sound effects in. Okay, right there. That is the function that looks like 128 times 1/2 to the x power. Or if you want to rewrite this, check this out. This is 128 times 1 to the x divided by 2 to the x. And you see 1 to any power is 1, so this is 128 divided by 2 to the x power. There's your function. 128 divided by 2 to the x power. All right, that's a nice way to write it there. All right, so there it is. There's your function, there's your graph. It's a decay function. It's a decay function, or what's called a decreasing function. And as you guys already know, decreasing function, the y values get smaller. All right, obviously as x gets bigger, all right, y gets smaller. Look at this. No. The y values decrease over time. And that's what happens in a tournament. This is a great example of what's called a decay function where things decrease really fast. All right. There you go. All right, this is Mr. Ainsworth here, and we are in the 9th lesson here, and I'll see you in the 10th lesson taking a look at another cool situation. I'll see you then.